Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So to introduce Harri's work, some of you, I guess the very few of you that were around in the very early days of the resurgence of deep learning back in ancient history, i.e. 2007 or something like that, will know that in the very early days, those of us who are around, we had a very strong emphasis on unsupervised learning. A few of us, I think Yosha, right, also Hong Lak, Mark Aurelio for their PhD thesis, did a lot of work on learning from unlabeled data. And then the whole community shifted because it worked so well to supervised learning. And recently, I think Harri developed an algorithm, pretty complicated algorithm, I should say. It's a bit of a mystery to some of us why it works so well, that is able to do remarkably good unsupervised learning. So excited to have him tell us about ladder networks, which feels like a exciting direction for doing much more with unsupervised learning, with unlabeled data, I should say. So Harri.
Thank you, Andrew. So, I'm Harri Valpola, the CEO and founder of the Curious AI company, and I'm going to tell you about the ladder network which we've developed. Here are the authors of the paper, and we are all based in Helsinki. Most of us are now with the Curious AI company, curiously. In the paper, we presented state-of-the-art results in several categories with fully connected and convolutional models with all labels and very few labels. And this was possible because we have finally got supervised and unsupervised learning to work together properly. And I'd like to highlight these results from Permutation Invariant MNIST. With all labels, the state-of-the-art results have come from fully supervised methods for the past several years. Now we are finally able to improve those results with unsupervised learning, and quite significantly. With 100 labels, the improvement is particularly dramatic. Our result is better than what deep learning got 9 years ago with 600 times more labels. Here's the fully connected network we use for permutation invariant MNIST. This animation shows standard supervised learning with backpropagation, so you get an idea of how forward computation, training, target, error, and backpropagation are visualized. And as you all know, this training results in a hierarchy of increasingly abstract features. In such training, humans are typically the ultimate source of the abstractions, but an interesting question is, could we find them in an unsupervised manner? Note that the lowest layers have details which are needed for local reconstruction, but higher layer abstractions are needed for bridging the gap over long distances in space and time and between modalities. Now, imagine you are a feature detector in the middle of the network, and you get all kinds of input patches in your receptive field. In the unsupervised case, how do you know which of all the features are relevant? In other words, where do you get your training targets from? The answer we and many others have proposed is that the targets can be derived from the context as expectations. In other words, the context can provide virtual labels for the feature detectors inside the network. This type of learning is well known to happen in hierarchical latent variable models. The only problem is nobody has so far managed to make inference and learning efficient and the model flexible all at the same time. So our solution is to directly learn the whole inference process rather than derive it from a statistical model. This solution is compatible with basically any deep learning architecture. For instance, we have used batch normalization and so on. We simply add a decoder with an auxiliary denoising task. This solution is efficient and scales just as fully supervised network. And in this talk, I'm going to explain how the ingredients of the ladder network are combined together. If I will have time left, I will also tell you about some cool new results. So let me start with denoising source separation. Let's take the feedforward network we saw earlier, zoom into one of the hidden units, and study its activation histogram. In a typical well-trained network, these histograms are typically non-Gaussian. So let's then visualize the joint distribution of two of the inputs to this unit. Of course, there are many other units, but here are two. Every dot is in this scatter plot is one observation. On any layer, there are typically very many units with all kinds of information. So if we take a random projection, we are likely to end up with a rather Gaussian distribution. In other words, a good feature detector will likely have a lower entropy than a reference Gaussian with the same variance. This difference is known as negentropy, and maximizing it is a well-known criterion in independent component analysis, sparse coding, and so on. So, So we can train a better feature by encouraging the activation distribution of the unit to be more non-Gaussian. Here you see how the projection vector turns as a result of such training. And what's more, we can backpropagate this training signal to lower levels of the network, which will be encouraged to transform the input distribution so that the detector will be even cleaner. This type of learning is pretty much what happens in hierarchical latent variable models. So now the question is, where do those red arrows come from? A well-known solution is the EM algorithm, where we alternate between E and M step. And the E step delivers the target for learning as an expectation, and it works as follows. We start with activations which are assumed to contain noise from noisy observations. We then postulate a parametric model for the observation distribution and train its parameters. This model can be hierarchical, so the model can represent very complex distributions. Then we take the model of the distribution and evaluate the posterior expectation analytically or approximately. The result is a training target which points towards higher prior probability. It's important to note here that this vector field is just an alternative way to represent the underlying data distribution. Me and my colleagues have been developing a technique called denoising source separation. And it's an efficient extension of many source separation techniques and builds upon the long research tradition in unsupervised learning in Helsinki. The key idea is to skip the probabilistic modeling part and represent explicitly the E-step, which can be seen as a procedure to denoise observations. It's often very easy and intuitive to define such a procedure, but now we will study another cool technique which is able to directly learn this procedure. Enter denoising auto-encoder. Denoising auto-encoders were developed here in Montreal in Joshua Bencher's group. They are a clever extension of autoencoders, and their task is not only to reconstruct, but also to denoise. And interestingly, this encourages the denoising autoencoder to implicitly model the complete joint distribution of the data. So let's see how it works. The basic idea is to corrupt the input with noise. This will move the data points in random directions. When we look at the whole data distribution, we can see that these random movements create a diffusion flow which points in a direction exactly opposite to the arrows we needed for the E-step. So now you can take an autoencoder and train it to denoise. Here you see how we present noisy inputs and clean targets to the network. This will directly learn the procedure for computing the E-step. With enough capacity, the network will be able to represent very complex E-steps and therefore implicitly capture very complex distributions, at least in theory, that is. One big problem with this setup still remains, and I'm going to explain how we solved it. The problem is this. Since the goal of the denoising autoencoder is also to reconstruct, it will have to hold on to all the details. It's not possible to reconstruct from the abstract features alone. This is not the type of abstraction hierarchy we at the supervised learning task would expect from the encoder. So supervised learning would like to discard the details while the autoencoder tries to preserve them. The solution I found for this is to imitate the computational structure of inference by message passing in hierarchical latent variable models. The encoder corresponds to the forward pass, which starts with the data, and where we essentially represent the likelihoods of latent variables given the data. And the decoder corresponds to the backward pass, which computes the final posterior probabilities. Crucially, these paths have to interact in much the same way as when we combine likelihood and prior to form the posterior. Another way to see this is that shortcuts from the encoder leak the details to the decoder, allowing higher layers of the encoder to discard them. Still, I find that it's more instructive to see this as an inference procedure rather than reconstruction. A related idea by Marco Aurelio Ranzato here and others focused on the invertibility of max pooling. They allowed the pooling indices to leak to the decoder. But now we leak much more, and we get away with that since the autoencoder is not just trying to copy, but also to denoise. This will encourage the network to implement complete Bayesian inference rather than just copy the noisy observations. So we have used unit-wise shortcut connections, and that corresponds to assuming conditionally independent latent variables. And any dependencies can and will still be modeled by the higher layers of the network, so this does not restrict the ability to represent complex nonlinear and non-Gaussian dependencies. And this is important for modeling complex real-world distributions. So, putting it all together, by asking this expressive network to denoise, we have turned it into a powerful distribution estimator. So now we are ready to connect the dots. We started by looking at how to train a single hidden unit, but let's now zoom out to consider training a whole layer of units, since large networks represent information with a distributed population of units. We take an encoder, which presumably implements likelihood computations, one way or another. Then we add a denoising auto-encoder on top of it for computing to learn the procedure for computing the E-step for the whole layer, by simply minimizing the squared error between the output and the likelihood computations and the denoised expectations provided by the implicit prior model. We train both parts of the model at the same time. The lower part learns like denoising source separation, and the upper part as a denoising autoencoder. In order to guarantee efficient learning in very deep models or with long time delays, we want to apply this type of learning on many or all of the layers of the encoder, in addition to standard supervised learning on top of the encoder. So if this encoder had, for instance, 20 layers, this would correspond to 21 learning problems. However, since our denoising autoencoder is compatible with abstraction hierarchies, we can combine all these networks into a single network, which looks like a large denoising autoencoder with lateral shortcut connections. A noise is added on each layer of the encoder, but since we still need the clean targets to train the decoder part, and therefore we evaluate the encoder also without noise. So, ladies and gentlemen, meet the ladder network. It's really simple but surprisingly powerful. On every layer, the clean encoder provides the target for the decoder and vice versa. We also have the supervised target on top of the noise encoder, and the corruption noise regularizes supervised learning in much the same way as dropout. For the price of 3 encoder passes, we are therefore able to implement learning on every layer of the network. There's a training cost right next to every parameter of the network. I have some time still, so I can explain these extras, right? I'll pick just one thing which I think is important, and that's semi-supervised learning of sequential data. We have some other results too, but no time. This is a real-world video clip from our collaborators at NVIDIA Helsinki. They have one of the best car detectors, but you can still see that still see how the detections flicker in and out of existence. So here, frame by frame, this flicker means that temporal context could be used for self-labeling. So in order to make efficient use of temporal context, which you can find, for instance, in these kinds of videos, we expand the ladder network in time dimension. We turn the ladder into a recurrent version by applying it on every time instance and connecting the encoder forward in time and the decoder backwards in time. Admittedly, it looks a bit messy and more like a scaffold than a ladder, but note that we had a very good reason for implementing temporal connections this way, because we are imitating the computational structure of message passing in state space models. So the encoder basically implements state estimation analogous to Kalman filtering, or the forward pass of Viterbi algorithm, if you work with hidden Markov models, and the decoder implements the backward pass, which is analogous to Kalman smoothing, or backward pass of Viterbi algorithms. So you see how this idea of message passing is general and makes it very easy to extend the ladder network. So now consider a simple illustrative example where we design a Markov chain out of MNIST digits. The hidden state corresponds to the digits class, and every state emits one of the digits in the dataset. All the information about the state is contained in the digit class. State transitions are probabilistic, with increment of 1 being the most probable, so 0, 1, 2, 3, 4, 5, and so on. But increments of 2 or 3 are possible too. As a side note, suppose you would like to learn this internal representation with a deep recurrent neural network that tries to learn to predict the next frame using the normal mean squared error loss. The trouble is, only the digit class is relevant for prediction, and therefore the optimal prediction just the class mean, even if the state transition is deterministic. A probabilistic increment means that the optimal prediction is a mixture of class means, and the trouble here is that while it is in principle possible to predict the joint distribution of the pixels of the next frame, it doesn't help much at the level of individual pixels. To prove the point, we will completely remove the whole subspace spanned by class means, making it impossible to predict anything at pixel level with mean squared error loss, even in principle. Yet a completely unsupervised recurrent ladder network learns a very good internal representation in a fully unsupervised manner. We don't have to tell it that there are 10 classes. It will automatically find a distributed representation which turns out to form 10 clusters. The distributed coding even captures similarities between similar-looking classes and classes that are close by in the sequence, much like in word embeddings. Finally, let me point out that in order to scale unsupervised learning to really large problems, I believe we have to pay attention to relevance. It's well known that in humans, attention plays an important role in learning. Luckily, the ladder network is fully compatible with such attentional modulation, as we have shown already in 2007 in a cortical model whose simplification the current ladder network is. So to summarize, we solved unsupervised learning by letting go of our inner statistician and letting the ladder network learn its own internal representations of distributions and how to do inference on them. The result is compatible, simple, efficient, and available for you to experiment with in GitHub. Thank you.
Do people have questions for Harri? Maybe let me ask, first something. I think you presented a few semi-supervised learning results.
Sure.
Where you had labeled MNIST digits and unlabeled MNIST digits.
Right.
Many years ago, Honglak and some of his collaborators proposed a related framework called self-taught learning, yes, which was a very simple insight that you can use unlabeled data from a totally random distribution, not just unlabeled images, but maybe random images downloaded off the internet. And the insight in self-taught learning was that you have essentially unlimited access to that data if you're not constrained to have it come from your test distribution. Have you done any experiments along that lines? Do you think it's promising?
We haven't, but I admit it would be very interesting. Like, we could try to just feed in with lots of data and then try to see what kind of representations it's learned. On the other hand, I believe that in order to get really, really good semi-supervised learning working, we have to do them together. So it's not enough to just first through unsupervised pre-training. It's important that supervised learning can give an idea of what's the rough solution, and unsupervised learning can then fine-tune this representation. So it's actually turning upside down what's been done before. So instead of unsupervised pre-training and supervised fine-tuning, it's like the other way around. Well, not supervised pre-training might not be a great idea in some cases. But anyway, I think that it's very important to have both of these tasks at the same time. Then again, unsupervised pre-training does help, no question about that.
Any other questions? All right. No? All right. Cool. Okay. Martin.
So my question is, if you didn't have the supervised information on the top of the labels, and you only had access to unsupervised data, what prevents the higher layers from not learning anything?
Oh, they do learn something, but I mean that if you have really large-scale problems like ImageNet, how do you know that the highest layers will be relevant for your task? Because there are so many different things to learn. If you think of natural video, for instance, and if you're only interested in cars and things related to traffic, you should definitely put that knowledge in. But yeah, in principle, you can just learn all kinds of things.
So I think what happens is that the lower layers want to minimize the denoising error of the upper layers, and in order to do that, they're trying to provide something that the upper layers can denoise.
Right.
Sort of.
All right, great. With that, let's thank Harri, and I'm definitely going to go to your GitHub repository and check everything out. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.